Hello, AUB students. Let's jump right into a high-impact review for your PHYS 210 final exam. We're going to break down the most important concepts, focusing on fluids and thermodynamics, to make sure you walk into that exam feeling totally prepared.
Look, I get it. These topics can be really tricky, but don't worry. We're about to cut through all that complexity and just zero in on the core principles that are going to make the biggest difference for you on exam day.
So, in the next few minutes, our goal is to lock in the absolute essentials. We'll kick things off with a quick mechanics warm-up to set the foundation before we tackle the main events. You ready? Let's dive in. Okay, first things first, let's make sure we've solidified the mechanics and energy principles that honestly everything else in this course is built on. Even though your final is going to be heavy on fluids and thermo, you'll see how concepts like work and energy pop up again and again. So let's just quickly run through these four big ideas. With a conservative force, like gravity, the path you take doesn't matter, only the start and end points. That's why the work over a closed path is always zero. Now, when non-conservative forces like friction get involved, that's when your total mechanical energy starts to decrease, usually lost as heat. And speaking of gravitational work, just remember, lifting something against gravity, that's negative work. Finally, for simple harmonic motion, or SHM, the key thing to remember is that acceleration is at its absolute max at the turning points, right when the object momentarily stops to change direction. Okay, with that foundation set, let's dive into our first major topic for the final, fluid mechanics. We're going to look at what fluids do when they're sitting still and when they're on the move.
Bernoulli's principle is, well, it's everything in fluid dynamics. It explains some really weird, counterintuitive stuff. Just burn this into your memory. For a fluid in motion, where the speed is high, the pressure is low. And where the speed is low, the pressure is high. It's a simple inverse relationship.
So you think you've got it? Let's put it to the test with a classic question, straight out of a past AUB final. You've got two balloons hanging there, and you blow a stream of air right between them. What happens? Take a second. Think about where you're changing the airspeed and how Bernoulli's principle applies. And yup, the answer is C. They move together. It seems backward, right? But as you see here, when you blow that air, you create a channel of high-speed flow. Bernoulli tells us this high-speed air has lower pressure. Meanwhile, the still air on the outside of the balloons is at a higher pressure, and that pressure difference literally pushes the balloons inward. It's a perfect real-world example of the principle. All right, time for the big one, thermodynamics. This is a huge part of your course, so we're going to tackle it law by law and really focus on the key ideas that you'll almost certainly see on the final. We have to start with the zeroth law. It sounds weird, right? The zeroth law? But it's actually the bedrock for everything else. It basically says if A is the same temperature as C and B is the same temperature as C, then A and B must be the same temperature. That simple idea is what lets us define and measure temperature consistently. Without it, a thermometer would be a useless concept. Okay, this right here, this is one of the most important takeaways for the first law, especially when you're talking about engines. For any cyclic process, and that just means a process that ends up right back where it started, the net change in its internal energy has to be zero. Why? Because internal energy is a state function. If you're back in the same state, you have to have the same energy. So what does that actually mean? Well, the first law is just conservation of energy. The change in internal energy equals the heat you add minus the work the system does. So if that change in energy over a full cycle is zero, it means every bit of net heat you put into the system must come out as net work done by the system. The energy has to balance out. This table, it's your new best friend. Seriously, it's a fantastic study tool that summarizes the key thing that's held constant in each process. The easiest one to remember is isovolumetric. If the volume doesn't change, no work can be done. It's impossible. And for an adiabatic process, no heat gets in or out. That has some really interesting consequences for work, which we're about to see. Okay, let's put this into practice with a very common exam-style question. Let's say you want to compress a gas to half its starting volume. Which way of doing it, isobaric, isothermal, or adiabatic, is going to make you, the external agent, do the most work? Think about it. In which process does the gas fight back the hardest? And the winner is adiabatic compression. Here's why. In an adiabatic process, you're not letting any heat escape. So all the work you're putting into the gas to compress it gets trapped and turns into internal energy. That makes the temperature shoot way up. And since pressure is related to temperature, the pressure also rises much, much more steeply than it would in an isothermal process, where you keep things cool. More pressure means you have to push harder, which means you do more work. All right, on to the second law, which is basically the universe's rulebook. It gives us the arrow of time. It tells us that in any real-world, irreversible process, the total entropy, you can think of it as disorder, of the universe always goes up. Things naturally get messier. The only time entropy changes zero is in a perfect, idealized, reversible, adiabatic process. And all this talk about efficiency and rules naturally leads us to heat engines and the ultimate benchmark, the Carnot engine. Now, you can't actually build a perfect one, but it represents the absolute theoretical maximum efficiency any engine can possibly have, operating between a hot place and a cold place. So, how does this perfect engine work? It's a four-step dance, all perfectly reversible. It starts with an isothermal expansion, grabbing heat from the hot reservoir. Then, an adiabatic expansion lets it cool down. After that, it does an isothermal compression, dumping waste heat into the cold reservoir. And finally, an adiabatic compression brings it right back to the start. It's this beautiful combination of two isotherms and two adiabats that makes it the most efficient cycle possible. Phew, we have covered a ton of ground, from basic mechanics through fluids and all the way to the laws of thermodynamics. So let's boil all this down into a final, clear game plan for your exam. This right here is your core concept cheat sheet. These are the absolute non-negotiable principles we've talked about. Focus your last bit of review on making sure you don't just know the principle, but you understand its application. If you can look at this table and confidently explain why each part is true, you are in amazing shape for this final. Okay, good luck on your final exam. You've put in the work. The key is to stay calm, break each problem down, and identify the core concept at play. Is this a Bernoulli problem? Is it about the first law? Is it about entropy? Find that core idea, and you'll find the solution. You've totally got this. Now go ace that exam.